Program must brought from disk into memory and placed within a process for it to be run. Main memory and the registers are only storage CPU can access directly. If the data are not in the memory, they must be moved from disk before the CPU can operate on them. The memory unit sees only a stream of memory addresses and the read or write request. So we can ignore how a program generates a memory address. We are interested only in the sequence of memory addresses generated by the running program. Registers are built into each CPU core and are generally accessible within one cycle of the CPU clock. So accessing data stored in register is very fast, only requires one cycle of the CPU clock. Accessing main memory is slower. So main memory is accessed by transaction on the memory bus. Completing a memory access may take many cycles of the CPU clock. In such cases, the processor normally needs to stall since it doesn't have the data required to complete the instruction that is executing. The situation is intolerable because of the frequency of memory access. The remedy is to add fast memory between the CPU and the main memory, typically on the CPU chip for fast access, such as a cache. The cache was built in between the main memory and the CPU register. Protection of memory is required to ensure correct operation. We first need to make sure that each process has a separate memory space. Separate per process memory space protects the processes from each other and is fundamental to having multiple processes loaded into the memory for concurrent execution. To separate memory space, we need the ability to determine the range of legal addresses that the process may access and to ensure that the process can access only these legal addresses. We can provide this protection by using two registers, usually a base and a limit. As illustrated in this figure, the base register holds the smallest legal physical memory addresses. The limit register specifies the size of the range. For example, if the base register holds 300040 and the limit register is 120900, then the program can legally access all addresses from 300040 through 420939. So the range is from base to base plus limit. CPU must check every memory access generated in the user mode to be sure it is between base and the limit for that user. If the memory access is out of range, it will result in a trap to the operating system, which treats the attempt as a fatal error. So this scheme prevents a user program from accidentally or deliberately modifying the code or data structures of either the operating system or other users. The base and the limit registers can be loaded only by the operating system, which use a special privileged instruction. User programs typically refer to memory addresses with symbolic names, such as in a C++ program, we use I, count, average temperature, etc. These symbolic names must be mapped or bound to physical memory addresses, which typically occurs in several stages. The addresses in the source program are generally symbolic, and the compiler typically binds this symbolic address to relocatable addresses. The linker or loader in turn binds the relocatable address to an absolute address. Each binding is mapping from one address space to another. The binding steps are compile time. If it is known at a compile time where a program will reside in physical memory, then absolute code can be generated by the compiler containing actual physical addresses. However, if the load address changes at some time later, then the program will have to recompile. Load time. If the location at which a program will be loaded is not known at compile time, then the compiler must generate relocatable code, which references addresses relative to the start of the program. If that starting address changes, then the program must be reloaded but not recompiled. Execution time. If a program can be moved around in memory during the course of its execution, then binding must be delayed until execution time. This requires special hardware, and it is the method implemented by most modern operating systems. The figure on the right shows various stages of the binding process and the units involved in each stage. Logical versus physical address space. The address generated by the CPU is logical address, while the address actually seen by the memory hardware is a physical address. Addresses bound at a compile time or load time have identical logical and physical addresses. Addresses created at the execution time, however, have different logical and physical addresses. In this case, the logical addresses is also known as a virtual address, and the two terms are used interchangeable by our text. The set of all logical address used by a program composes the logical address space, and the set of all corresponding physical address compose the physical address space. The runtime mapping of logical to physical addresses is handled by the Memory Management Unit, MMU. The base register is now called relocation register. The value in the relocation register is added to every address generated by a user process at the time the address is sent to the memory. For example, if the base is at 14,000, then an attempt by the user to address location 0 is dynamically relocated to location 14,000, and access to location 346 is mapped to the location 14346. Note that user program never see physical addresses. User program work entirely in logical address space, and any memory references or manipulations are done using purely logical addresses. Only when the address gets sent to the physical memory chips is the physical memory address generated. Rather than loading an entire program into memory at once, dynamic loading loads up each routine as it is called. The advantage is that unused routines need never be loaded, reducing total memory usage and generating faster program startup time. The downside is the added complexity and overhead of checking to see if a routine is loaded every time it is called, and loading it up if it is not already loaded. With static linking, library modules get fully included in executable modules, wasting both disk space and the main memory usage, because every program that included a certain routine from the library would have to have their own copy of that routine linked into their executable code. With dynamic linking, however, only a stub is linked into the executable module, containing references to the actual library module linked in at runtime. The method saved disk space because the library routines don't need to be fully included in the executable modules, only the stubs. We will also learn that if the code section of the library routines is reentrant, meaning it doesn't modify the code while it runs, make it safe to re-enter it, then main memory can be saved by loading only one copy of dynamically linked routines into memory and sharing the code amongst all processes that are concurrently using it. Each process would have their own copy of the data section of the routines, but that may be small relative to the code segments. Obviously, the operating system must manage the shared routines in memory. An added benefit of dynamically linked library like DLL, also known as a shared library or shared object on Unix system, involves easy upgrade and updates. When a program uses a routine from a standard library and the routine changes, then the program must be rebuilt or relinked in order to incorporate the changes. However, if DLL are used, then as long as the stub doesn't change, the program can be updated merely by loading new versions of the DLL onto the system. Version information is maintained in both the program and the DLLs, though that program can specify a particular version of the DLL if necessary. In practice, the first time a program calls a DLL routine, the stub will recognize the fact and will replace itself with the actual routine from the DLL library. Further calls to the same routine will access the routine directly and not incur the overhead of the stub access. Main memory must support both operating system and the user process, so that resource is limited and we must use it efficiently. Contiguous allocation is one early method. The memory is usually divided into two partitions, one for the operating system and one for the user process. We can place the operating system in either low memory address or high memory address. In the contiguous memory allocation, each process is contained in a single contiguous section of memory. In this memory allocation, all the available memory space remains together in one place, which implies that the freely available memory partitions are not spread over here and there across the whole memory space. Registers are used to protect user process from each other and from changing operating system code and data. We have a base or relocation register contains value of smallest physical address, the starting physical address, and the limit register contains range of logical address. Each logical address must be less than the limit register. So MMU maps logically address dynamically. When the CPU scheduler selects a process for execution, the dispatcher loads the relocation and the limit registers with the correct values as part of the context switch. Because every address generated by a CPU is checked against these registers, we can protect both the operating system and the other user's programs and the data from being modified by this running process. One of the simplest methods of allocating memory is to assign process to variably sized partitions in memory, where each partition may contain exactly one process. In this variable partition scheme, the operating system keeps a table indicating which part of memory are available and which are occupied. Initially, all memory is available for user process and is considered one large block of available memory, a whole. Eventually, you will see memory contains a set of holes of various sizes. This figure depicts this scheme. Initially, the memory is fully utilized, containing process 5A and 2. After process A leaves, there is one contiguous hole. Later on, process 9 arrives and is allocated memory. Then process 5 departs, resulting in 2 non-contiguous holes. When a process arrives, it is allocated memory from a hole large enough to accommodate it. When process finishes work, it exits, freeing its partition and the adjacent free partitions combined. The operating system maintains information about the allocated partitions and the free partitions. Dynamic storage allocation problem concerns how to satisfy a request of size n from a list of free holes. There are many solutions to this problem. The first fit, best fit, and the worst fit strategies are the ones most commonly used to select a free hole from a set of available holes. First fit is to allocate the first hole that is big enough. Best fit is to allocate the smallest hole that is big enough. The worst fit is to allocate the largest hole. Simulations have shown that both first fit and the best fit are better than worst fit in terms of decreasing time and the storage utilization. Neither first fit nor best fit is clearly better than the other in terms of a storage utilization, but first fit is generally faster. All the memory allocation strategies suffer from external fragmentation. Though first and the best fits experience the problems more than worst fit. External fragmentation means that the available memory is broken up into lots of little pieces, none of which is big enough to satisfy the next memory requirement, although the sum total could. The amount of the memory lost to fragmentation may vary with algorithm, usage patterns, and some design decisions, such as which end of hole to allocate and which end to save on the free list. Statistically analysis of a first fit, for example, shows that for n blocks of allocated memory, another 0.5 n will be lost to fragmentation. Internal fragmentation also occurs with all memory allocation strategies. This is caused by the fact that the memory is allocated in blocks of a fixed size, while the actual memory needed will rarely be that exact size. For a random distribution of memory requests, on the average, half of the block will be wasted per memory request, because on the average, the last allocated block will be only half full. The same effect happens with hard drives, and that modern hardware gives us increasing larger drives and memories at the expense of ever larger block sizes, which translates to more memory lost to internal fragmentation. Some systems use variable size blocks to minimize losses due to internal fragmentation. If the programs in memory are relocatable using execution time address binding, then the external fragmentation problem can be reduced by compaction. For example, moving all process down to one end of physical memory. This only involves updating the relocation register for each process, as all internal work is done using logical addresses. Another solution, as we will see in upcoming sections, is to allow process to use non-contiguous blocks of a physical memory with a separate relocation register for each block. Paging is a memory management scheme that allows process physical memory to be discontinuous and which eliminates the problems with fragmentation by allocating memory in equal-sized blocks, known as pages. Paging eliminates most of the problems of other methods discussed previously and is the predominant memory management technique used today. The basic idea behind paging is to divide physical memory into a number of equal-sized blocks called frames, and to divide a program logical memory space into blocks of the same size called pages. Any page from any process can be placed into any available frame. The page table is used to look up what frame a particular page is stored in at the moment. A logical address consists of two parts, a page number in which the address resides, and an offset from the beginning of that page. The number of bits in the page number limits how many pages a single process can address. The number of bits in the offset determines the maximum size of each page, and it should correspond to the system frame size. The page table maps the page number to a frame number to yield a physical address, which also has two parts, the frame number and the offset within that frame. The number of bits in the frame number determines how many frames the system can address, and the number of bits in the offset determines the size of each frame. Frame numbers and the frame sizes are determined by the architecture, but are typically powers of 2, allowing addresses to be split at a certain number of bits. For example, if the logical address size is 2 to m and the page size is 2 to n, then the high order m minus n bits of a logical address designate the page number, and the remaining n bits represent the offset. Also, the number of bits in the page number and the number of bits in the frame number don't have to be identical. The former determines the address range of the logical address space, and the latter relates to the physical address space. When a process arrives in the system to be executed, its size expressed in page is examined. In this example, we have a new process, have page 0, 1, 2, 3, so it has 4 pages. Each page of the process needs 1 frame. Thus, if the process requires n pages, at least n frame must be available in the memory. So in this example, we can see the free frame list. All those frames in gray color, they are available. So 14, 13, 18, 20, and 15, they are available. The first page of the process is loaded into one of the allocated frames, and the frame number is put in the page table for this process. So we can see the page 0 is put in frame 14. Also, the frame number is put into the page table. The next page is loaded into another frame. Its frame number is put into the page table, and so on. Processes are blocked from accessing anyone else's memory because of their memory requests are mapped through their page table. There's no way for them to generate an address that maps into other process memory space. The operating system must keep track of each individual process page table, updating it whenever the process page gets moved in and out of memory, and applying the correct page table when processing system calls for a particular process. This will increase the overhead involved when swapping process in and out of the CPU. The operating system can also keep a frame table. The frame table has one entry for each physical page frame, indicating whether the latter is free or allocated, and if it is allocated to which page of process. Page lookups must be done for every memory reference, and whenever a process gets swapped in or out of the CPU, its page table must be swapped in and out too, along with the instruction register, etc. It is therefore appropriate to provide hardware support for this operation in order to make it as fast as possible and to make process switches as fast as possible also. One option is to use a set of registers for the page table. An alternate option is to store the page table in main memory and to use a single register called Page Table Base Register, PTBR, to record where in memory the page table is located. So process switching is faster because only the single register needs to be changed. However, memory access just got half as fast because every memory access now requires two memory access, one to fetch the frame number from memory, and then another one to access the desired memory location. This solution to this problem is to use a very special high-speed memory device called Translation Look Aside Buffer, TLB. The benefit of the TLB is that it can search an entire table for a key value in parallel, and if it is found anywhere in the table, then the corresponding lookup value is returned. Please click on the link to view the video. You can take a look at the effective memory access time in the video, but later we will view this in the new book edition. The new book edition ignores the TLB access time. The TLB is very expensive, however, and therefore very small, not large enough to hold the entire page table. It is therefore used as a cache device. Addresses are first checked against the TLB, and if the information is not there, a TLB missed, then the frame is looked up from main memory and the TLB is updated. If the TLB is full, then replacement strategies range from least recently used, LRU, to random. Some TLB allows some entries to be whiled down, which means that they cannot be removed from the TLB. Typically, this would be kernel frames. Some TLBs store address space identifier, ASIDs, to keep track of which process owns a particular entry in the TLB. This allows entries from multiple processes to be stored simultaneously in the TLB without granting one process access to some other process memory location. Without this feature, the TLB has to be flushed clean with every process switch. The percentage of time that the desired information is found in the TLB is termed the hit ratio. You should have viewed the video on the effective access time in previous slide. In this edition book, it ignores the 20 nanoseconds. So if we have 80% hit ratio and we have 10 nanoseconds to access memory, if we found the desired page in TLB, then mapped memory access just takes 10 nanoseconds. Otherwise, we need a 2-cycle to memory access, which is 20 nanoseconds. So the effective access time is 0.8, that's 80%, multiply 10, that's 1 memory access time. Then plus the miss time, which is 20% miss rate, multiply 2 memory access time, which is 20 nanoseconds. So the total equal 12 nanoseconds. That implying if we totally have a TLB hit, like 100%, multiply 10, that will be 10 nanoseconds. But now it's 12 nanoseconds. So it's implying 20% slowdown in access time. If the hit rate increased to 99%, the effective access time is 10.1 nanoseconds, so implying only 1% slowdown in access time. The page table can also help to protect process from accessing memory that they shouldn't, or their own memory in ways that they shouldn't. A bit or bits can be added to the page table to classify a page as a read-write, read-only, read-write-execute, or some combination of these sort of things. Then each memory reference can be checked to ensure it is accessing the memory in the appropriate mode. Valid, invalid bits can be added to mask off entries in the page table that are not in use by the current process. Note that the valid-invalid bits described above cannot block all illegal memory access due to internal fragmentation. Areas of memory in the last page that are not entirely filled by the process and may contain data left over by whoever used that frame last. Many processes don't use all of the page table available to them, particularly in modern systems with very large potential page tables. Rather than waste memory by creating a full-size page table for every process, some systems use Page Table Length Register, PTLR, to specify the length of the page table. In this example, we have 6 pages from page 0 to page 5 for a process. So address in page 0, 1, 2, 3, 4, and 5 are mapped normally through the page table. Any attempt to generate an address in page 6 and 7, however, will find that valid-invalid bits is set to be invalid, and the computer will trap to the operating system invalid page reference. Paging systems can make it very easy to share blocks of memory by simply duplicating page numbers in multiple page frames. This may be done with either code or data. If code is reentrant, that means it doesn't write or change the code in any way. It is non-self-modifying, and it is therefore safe to re-enter it. Most importantly, it means the code can be shared by multiple processes, as long as each has their own copy of the data and the registers, including the instruction register. In this example, we see 3 processes sharing the page for the standard C library, libc. Reentrant code is non-self-modifying code. It never changes during execution. Thus, two or more processes can execute the code at the same time. Each process has its own copy of registers and the data to hold the data for process execution. The data for two different processes will, of course, be different. Only one copy of the standard C library need to be kept in physical memory, and the page table for each user process maps onto the same physical copy of libc. Thus, to support 40 processes, we need only one copy of the library instead of 40 copies. Most modern computer systems support logical address space of 2 to 32 to 2 to 64, like 32 bits and 64 bits. With the 32 bits address space in the 4K page size, this leaves 2 to 20 entries in the page table. So 2 to 32 divided by 2 to 12, that's a 4K, equals 2 to 20 entries in the page table. At the 4 bytes per entry, though this amounts to a 4 MB page table, which is too large to reasonably keep in contiguous memory, and too expensive to swap in and out of memory with each process switch. Note that with 4K pages, they will take 1024 pages just to hold the page table. We will explore some of the most common techniques for structuring the page table, including hierarchical paging, hashed page tables, and the inverted page tables. One simple solution to this problem is to divide the page table into smaller pieces. We can accomplish this division in several ways. One way is to use a two-level paging algorithm in which the page table itself is also paged. For example, the 20 bits described above could be broken down into two 10-bit page numbers. The first identifies an entry in the outer page table, which identifies where in memory to find one page of an inner page table. The second 10 bits finds the specific entry in that inner page table, which in turn identifies a particular frame in physical memory. The remaining 12 bits of the 32-bit logical address are the offset within the 4K frame. Because address translation works from the outer page table inward, this scheme is also known as a forward mapped page table. Even two-level paging scheme is not sufficient. If page size is 4 KB, which is 2 to 12, then page table has 2 to 52 entries. So we can get this because it's a 64 bits logical address space. So 2 to 64 divided by the page size, which is 2 to 12, equal 2 to 52. If two-level scheme, inner page tables can be 2 to 10 4 bytes entries. So the address would like the inner page is 10, then the outer page is 42, then the offset is 12. We can divide the outer page table. For example, we can page the out page table, giving us 3-level paging scheme. Suppose that the outer page table is made of standard pages, like 2 to 10 entries, or 2 to 12 bytes. In this case, the 64-bit address space is still hunting. The outer page table is still 2 to 34 bytes, which is 16 gigabytes in size. For 64-bit architecture, hierarchical page tables are generally considered inappropriate. The algorithm works as follows. The virtual page number in the virtual address is hashed into the hash table. The virtual page number is compared with field 1 in the first element in the linked list. If there's a match, the corresponding page frame, which is field 2, is used to form the desired physical address. If there's no match, subsequent entries in the linked list are searched for a matching virtual page number. A variation of this scheme that is useful for 64-bit address spaces has been proposed. This variation uses clustered page tables, which are similar to hashed page tables, except that each entry in the hash table refers to several pages, such as 16, rather than a single page. Therefore, a single page table entry can store the mappings for multiple physical page frames. Clustered page tables are particularly useful for sparse address spaces, where memory references are non-contiguous and scattered throughout the address space. Another approach is to use an inverted page table. Instead of a table listing all of the pages for a particular process, an inverted page table lists all of the pages currently loaded in memory for all processes. For example, there is one entry per frame instead of one entry per page. Access to an inverted page table can be slow, as it may be necessary to search the entire table in order to find the desired page or to discover that it is not there. Hashing the table can help speed up the search process. Inverted page table prohibit the normal method of implementing shared memory, which is to map multiple logical pages to a common physical frame, because each frame is now mapped to one and only one process. This example is an IBM system. Each virtual address in the system consists of PID, page number, and offset. Each inverted page table entry is a pair of process ID and the page number, where the process ID assumes the role of the address space identifier. When a memory reference occurs, part of the virtual address consisting of process ID, page number is presented to the memory subsystem. The inverted page table is then searched for a match. If a match is found, let's say at entry I, then the physical address I offset is generated. If no match is found, then illegal address access has been attempted. So an inverted page table has one entry for each real page of memory. Each entry consists of the virtual address of the page stored in that real memory location, with information about the process that owns the page. So from in this graph, we can see the invert page has a PID and the page number. Thus, only one page table is in the system, and it has only one entry for each page of physical memory. The modern 64-bit CPU and operating system, Solaris, running on the Spark CPU, is a fully 64-bit operating system and as such has to solve the problem of virtual memory without using up all of its physical memory by keeping multiple levels of page tables. Its approach is a bit complex but solves the problem efficiently using hashed page tables. There are two hash tables, one for the kernel and one for all user process. Each maps memory address from virtual to physical memory. Each hash table entry represents a contiguous area of mapped virtual memory, which is more efficient than having a separate hash table entry for each page. Each entry has a base address and a span indicating the number of pages the entry represents. TLB holds translation table entries, TTES, for fast hardware lookup. So recall, what is TLB? That's a translation look aside buffer, TLB. It's a memory cache that stores the recent translations of virtual memory to physical memory. A cache of this TTES resides in a translation storage buffer, TSB, which includes an entry per recent accessed page. When a virtual address reference occurs, the hardware searches the TLB for a translation. If none is found, the hardware walks through the in-memory of TSB looking for the TTE that corresponds to the virtual address that caused the lookup. This TLB walk functionality is found on many modern CPUs. If a match is found in the TSB, the CPU occupies the TSB entry into the TLB and the memory translation completes. If no match is found in the TSB, the kernel is interrupted to search the hash table. The kernel then creates a TTE from the appropriate hash table and stored in the TSB for automatic loading into the TLB by the CPU memory management unit. Finally, the interrupt handler returns control to the NMU, which completes the address translation and retrieves the requested byte or word from main memory. Process instructions and the data they operate on must be in memory to be executed. However, a process or a portion of process can be swapped temporarily out of memory to a backing store and then brought back into the memory for continued execution. In this figure, we can see in the main memory, the process 1 is swapped out to backing store, and the process P2 is swapped in from backing store into the main memory. Swapping makes it possible for the total physical address space of all processes to exceed the real physical memory of the system, thus increasing the degree of multi-programming in a system. Roll in, roll out, swapping variant used for priority-based scheduling algorithm. Lower priority process is swapped out so higher priority process can be loaded and executed. The majority part of a swap time is transfer time. The total transfer time is directly proportional to the amount of memory swapped. The system maintains a ready queue of ready-to-run processes which have memory images on disk. Does the swapped out process need to swap back into the same physical addresses? It depends on the address binding method. Also consider the pending input-output to or from process memory space. Standard swapping was used in traditional Unix system, but it is generally no longer used in contemporary operating system because the amount of time required to move entire process between memory and the backing store is prohibited. Most systems, including Linux and Windows, now use a variant of swapping in which pages of a process rather than entire process can be swapped. In fact, the term swapping now generally refers to standard swapping, and the paging refers to swapping with paging. A page out operation moves a page from memory to the backing store. The reverse process is known as a page in. Swapping with paging is illustrated in this figure, where a subset of pages for process A and B are being paged out and paged in respectively. Most operating systems for PC and the servers support swapping pages. In contrast, mobile systems typically don't support swapping in any form. Mobile systems generally use flash memory rather than more spacious hard disk. Only a limited number of writes is allowed because the poor throughput between flash memory and the CPU on mobile platform. Instead of using swapping, when free memory falls below a certain threshold, Apple's iOS asked the application to voluntarily relinquish allocated memory. Read-only data are removed from main memory and later reloaded from flash memory if necessary. Data that have been modified are never removed. However, any applications that fail to free up sufficient memory may be terminated by the operating system. Android adopts a strategy similar to that used by iOS and may terminate a process if insufficient free memory is available. However, before terminating a process, Android writes its application state to flash memory so that it can be quickly restarted. The architecture of Intel chips has dominated the personal computer. Pentium CPUs are 32-bit and called IA32 architecture. Current Intel CPU are 64-bit and called IA64 architecture. In this section, we will examine address translation for both IA32 and the x86 64 architectures. So we present the major memory management concept of this Intel CPU. The Pentium CPU provides both pure segmentation and segmentation with paging. In the latter case, the CPU generates a logical address, segment offset pair, which the segmentation unit converts into a logical linear address, which in turn is mapped to a physical frame by the paging unit, as shown in this figure. The Pentium architecture allows segments to be as large as 4 KB. That's 24 bits of offset. Process can have as many as 16K segments, divided into two AK groups. AK private to that particular process, stored in local descriptor table, LDT. AK shared among all processes, stored in the global descriptor table, GDT. Logical addresses are the pairs of a selector and an offset, where the selector is made of 16 bits. So in this graph, we can see we have a 16 bits. a 13-bit segment number, so that's up to 8K. The second part is a 1-bit flag for LDT versus GDT, and the remaining 2 bits for protection code. The linear address given to paging unit generates physical address in main memory. Paging units form equivalent of MMU, memory management unit. The page sizes can be 4KB or 4MB. The descriptor table contains 8-byte descriptions of each segment, including base and the limit registers. Logical linear addresses are generated by looking the selector up in the descriptor table and adding the appropriate base address to the offset, as shown in this figure. Pentium paging normally use a 2-tier paging scheme, with the first 10 bits being a page number for an outer page table, like a page directory, and then the next 10 bits being a page number within one of the 1024 inner page tables, leaving the remaining 12 bits as an offset into a 4K page. The IA32 address translation is shown in this figure. The 10 high-order bits reference an entry in the outermost page table, which IA32 terms as a page directory. So we see the bits from 31 to 21 is point to the page directory. The CR3 register points to the page directory for the current process. The page directory entry points to an inner page table that is indexed by the contents of innermost 10 bits in the linear address. Finally, the low-order bits 0 to 11 refer to the offset in the 4KB page pointed to in the page table. As software developers began to discover the 4 GB memory limitations of 32-bit architecture, Intel adopted a page address extension, PAE, which allows 32-bit processors to access a physical address space larger than 4 GB. The fundamental difference introduced by PAE support was that the paging went from a 2-level scheme, as the previous slide, to a 3-level scheme, where the top 2 bits refers to a page directory pointer table. In this figure, it illustrates a PAE system with 4 KB pages. PAE also supports 2 MB pages. Current generation is Intel x86 architecture. 64-bit address space can yield 16 exabytes. However, in practice, far fewer than 64 bits are used for address representation in current design. The x86 64 architecture currently provides a 48-bit virtual address with support for page size of 4 KB, 2 MB, or 1 GB using 4 levels of paging hierarchy. In this figure, it shows the linear address. Because this addressing scheme can use PAE, virtual addresses are 48 bits in size, but support 52-bit physical address. ARM architecture is for mobile systems like Apple iOS and Google Android. It's modern, energy efficient, and a 32-bit CPU. The ARM v8 has 3 different translation granules, 4 KB, 16 KB, and 64 KB. Each translation granule provides different page sizes, as well as larger sections of contiguous memory, known as regions. For 4 KB and 16 KB granules, up to 4 levels of paging may be used, with up to 3 levels of paging for 64 KB granules. The 4-level hierarchical paging structure for the 4 KB translation granule is illustrated in this figure. The TTBR register is the translation table base register and points to the level 0 table for the current thread. The ARM architecture also supports 2 levels of TLBs. At the inner level are 2 micro TLB, a TLB for data and another for instructions. The micro TLB supports ASID as well. At the outer level is a single main TLB. Address translation begins at the micro TLB level. In the case of a miss, the main TLB is then checked. If both TLBs misses, a page table walk must be performed in hardware.